Your eyes were bawling while you were doing electricity. To be honest, I hated the class that I took, but I love the book that I'm reading. But yeah, hi Thunder, hi Yanis, and hey Country Tyler. That was Daisy, yeah. So another reading group. Not sure if people are going to be around, but we always do it anyway. Let me hop in the Discord. Get it so I can actually see if someone jumps in. Okay. Sure, Thunder, because no one's hopped in to proceed with the actual group yet, so if we can do it quick, I'll try to get it done now. And my break was good. I might still take a bit more time next week too, but I've been needing to like the big thing I've been needing to do. I've been applying to jobs and researching grad schools for a couple months now, and I with how much I was streaming, I just didn't have the energy to do it, so I had to take some time to prioritize that. Oh gosh, what is happening here? Not the best with circuits, but maybe Fenbox will jump in and save me. He's around. No, I mean, I'll try my best anyway. Saw me cooking food look tasty. Oh, the things that I posted. Yeah, I went a little crazy with cooking over the weekend. No worries about the quality. I know it's I assume it's from like an online like homework website where it's hard to like zoom things in. So what are we looking at here? Which about an experiment to obtain current voltage data for a resistor R. Figure 1 shows a current voltage data for R. And because of Ohm's law, oh god, freaking Excel drop, bro. V equals IR. I would expect a linear relationship between voltage and current. So voltage on the horizontal axis, interesting. And this looks approximately linear, but not perfect. But that's okay because this is like real data, so we don't expect it to be perfect. And sorry, my friend just texted me. I need to get back to him. Hey, Fembucks. I was just trying to look at this question quick from Thunder before getting to the actual group. Feel free to hop in though if you want. It's an EMF question further on. Oh, okay. I do have a time limit today. I'll still be able to do the entire reading group and hopefully a bit of math help after, but I'm gonna go watch a movie with friends tonight. One of the circuits A to D shown in figure 2 was used to obtain the current voltage data in figure 1. The maximum resistance of resistor P is twice the maximum resistance of resistor P is twice the oh god. This battery has an EMF 14.6 volts and negligible internal resistance. Hey Hayden, we're doing well. Discuss or deduce which one of the circuits was used to directly obtain the current voltage data in figure 1. You should include your answer an explanation of why each of the other circuits is not suitable to obtain the data directly from the voltmeter and ammeter readings. Ooh. Okay. Which one of these circuits now are these the same? They're not quite the same arrangements. Oh, this B looks different. Oh, Hayden, I just said I hope that you're doing well. Um, has to be B or D, then you pray, I guess, right? Yeah, this one, I don't know. I don't have an intuition here. I was doing some coding today and managed to 403 forbidding kitten X error. I love the kittens, bro. Cats are rad as hell. I agree. You said mark scheme, but it's super unhelpful. Yeah, so it seems like it's asking like where should you position your voltmeter and ammeter here to get good data? The positioning of the voltmeter in A looks terrible. What was its syntax? Like, I don't know what the hell the voltmeter is actually measuring here. I guess the resistance across, or I guess the voltage across that resistor R. Maybe it's not so terrible. Use the wrong slash, classic. Um, Alex, you're agreeing it's either B or D. The mark scheme says that D is correct. So I assume like when he's or the other one's given non-linear relationship is to show. I don't know how it would happen, but or or maybe the instrument's just being used completely wrong. Ammeter's in the wrong place in A. Okay, yeah, it's we're trying to measure the resistance. What are we trying to do? For the so we're measuring things about the resistor R down here. Okay, so yeah, the ammeter is just completely out of sorts for number A, answer A. It needs to be in series with R. Circuit B is incorrect because the voltage range shown data cannot be produced. Why? The voltage range shown in the data cannot be produced. Because B, P, and R are in series. Yeah, the only difference between B and D is whether they're in series or parallel here. Otherwise, they're the exact same answer. Yeah, the variable resistor P is kind of throwing me off too. You even get a reading of 0 from circuit D. Well, there isn't an actual 0 reading. It's close to 0. Oh wait, there is a 0, 0 data point hidden. Oh no, I can't tell if that's the axes going a little bit past or not. There is a 0 reading? Okay. Oh, sorry, yeah, I wasn't quite, my cam was blocking it. I should really just resize it so that I don't have overlap, but it does look like there's a little data point right in there. We can only get down to voltage of 0 if the variable resistor is connected on the right to the battery. Down to voltage of 0. So Zero voltage means zero resistance. Get why it's not A, B, and C, but you don't understand how D works. And I assume the key is in what Fembox is saying. With being in series versus being in parallel. I don't quite get why this circuit is going halfway into the resistor P though. I don't get what that means. Like, does this resistor have two inputs and one output?
Hey, Don.
Hey, Fembox.
Yeah, that resistor at P is a variable resistor, and if you look really closely, it's like a little arrowhead underneath it, touching it in the middle.
Yeah.
And what that means is you can kind of slide that arrow along from the left to the right and change the resistance, like how much of the current has to go through the resistor.
Oh.
Yeah, it's a variable resistor.
Okay. And I was trying to figure out why these need to be in parallel to have 0 volts.
Yeah, so in circuit D, yeah, I see it now. So in circuit D, if you slide that arrow all the way to the right, then the battery is going to go right through resistor P, right? And it's never going to come down through resistor R. Like the current from the battery will just go through resistor P, and then it'll short back right back to the battery. So you won't get any current through R in that case. Whereas if you slide that resistor all the way to the left, then the current will split, right? Some of it will go through R and some of it will go through P.
I don't see that, or I guess I don't quite get what you're saying. Like, so, like, I'm trying to, like, draw, like, the actual arrow, like, should be on the right side of P here, and it's going through the entire, it's going to experience more resistance? Like, if we were to imagine
So where you've drawn the red arrow over on the right side, right? So now just look at that circuit. What we've done is we've shorted out resistor R, right? So the battery sees resistor P. The current from the battery comes through resistor P from the left to the right. And when it gets to the right side, it can choose to go down through resistor R or just to go right and not go through resistor R, right? So we've shorted out resistor R completely in that configuration.
Oh, I thought I had the current going the wrong way in my head. The current is going around, like, this way?
I guess it doesn't matter which way. Either
Or is
way,
that the
we've
way to make it
shorted out.
work? Okay.
Yeah, either way, we've shorted out R.
So if we're shorting it by sliding L to the right, the current is going around that way, though, because it's only ever going to follow this top loop, the current.
Yeah.
Okay. And that would give us 0 voltage drop across R?
Yeah. Whereas in circuit B, no matter how we slide that variable resistor, the current always has to come down through R, right? So we always have to have some voltage drop across R. It can never be 0 in that case.
Okay. Hit critical. And so, Thunder, I think what's happening is that we imagine sliding this arrow with A, like, to the left and right on this variable resistor P to change its resistance. And the point is that if we slid it all the way to the right, like how I had drawn, if the current, we imagine it going counterclockwise, the current has no reason to ever go down into the resistor R. It's just going to get cut out of the circuit completely, or it essentially won't be part of the circuit. And so that's what Fembox means with, like, shorting it. It's basically no current is going to go through it. It has no reason.
A short circuit means you have like a wire. You have like 0 resistance. Why do they call it short? I don't know. Maybe it means the current found a shorter way to get back to where it was trying to get to. I don't know, like a shortcut. It's the opposite of an open circuit.
It's the maximum 14.6 volts. Okay, yeah. So I guess tiny bit busy. Shorting means what? It means that you've effectively, if you short a circuit, it means that you're kind of taking a shortcut. So in this case, we're saying we're shorting out R because if you slide it all the way to the right, you basically completely avoid R. The current is never going to flow through it. And sorry, Femox, what?
Yeah, I was just going to say it's like we've put a wire across the end points of R, right? Resistor R. We've sort of connected the two endpoints with a wire. That's what it means to short those two nodes in the circuit. There's a wire connecting the two nodes, so there's a short from one node to the other node.
Yeah. In critical, I can look at it more like I could get like one of those lines is missing a semicolon, but are you trying to work on it for yourself too? Because like I don't just want to do the entire thing for you. It's like we skip the parallel circuit. Yeah, like it's never going to come down through this. It's only ever going to go through P. That's in the scenario we drag this variable resistor all the way to the right. Which I think would be the least resistance if we do take the current to go in this direction.
Yeah, I wondered.
Okay, so it sounds like Thunder got what they need. I think it would have to be, because if you go all the way to the left, I think that would be infinite resistance, and the current should all go down into R. Or very high resistance.
If you go all the way to the left, all the way to the left means now we have R and P in parallel. Whereas when you go all the way to the right, you just have P in parallel. Well, you have P in, I don't know, what would we say? You just have P. R is gone. So we can kind of vary how much current kind of comes down through resistor R by sliding that arrow to the left and right.
Also, it is literally like moving the wire along the resistor. I thought it was just like a metaphor, but it's like it's siphoning off some current from P.
Yeah, it's kind of like I've seen one of them in a lab, and it was just like a big coil of copper wire wound around a cylinder or something, and it has a point on the left and a point on the right, and it has a point in the middle that's kind of connected back to the point on the right that you can slide along. A rheostat? Yeah, that might be another word for it, a rheostat.
Oh, okay. Good to know.
Yeah, if you Google like images of variable resistor, you'll kind of see what one looks like. A lot of them are kind of little things.
The linear one is what I was imagining. Sorry, what?
I was going to say a lot of them are those little things that look like they're circles, and I think you can like turn a dial to change how much resistance it's being seen between the ends. Oh, you know what I think of? Know what I think it's called? I think it's called a potentiometer. I think that's what they call them, or they call it a pot. Sometimes they used to call it a pot.
Yeah,
so it's kind of like when let's look at that. Yeah, look at that picture, like the fifth one along. Yeah, right there. What is a potentiometer? Yeah, that one. Oh, it does have an RH on it. Look. Yeah, maybe.
Oh yeah, RH.
Maybe Thunder's got that. So RH might be, maybe the rheostat is what that thing is. So maybe a potentiometer has a rheostat inside it.
Interesting. Okay. Yeah, rheostat, they say it right there.
Hmm. Sliding contact. Yeah.
That's cool. I didn't know this thing existed. It makes sense. Okay. Thank you for the saving that question, Felix. I don't know that I could have like done that my own.
Yeah, no problem.
Um, so
Makes up for the fact that I'm like only halfway through this week's chapter so far.
no worries. I put the Excalibur link in like the chat for the voice chat again. So like there's a little like chat bubble if you hover over the header of the voice chat.
Okay.
And before I forget to mention it, there's only 11 chapters in the book in total, and so now we're working on chapter 5. That's a little over halfway if we did every single chapter, but I don't think we need to do every single chapter. I kind of just want to get to Maxwell's equations.
Mm-hmm.
So we went to ask Dr. Cook what's a good like route to take there, or if we do need to hit every single chapter between there. But oh, hey, there's Cook.
Yeah.
So Cook, I remember like a while ago you mentioned this book that we wouldn't necessarily need to hit to like read every chapter of this book to get the overall point. And I'm just kind of thinking about like how far we want to go in it. It's like I'd like to get to chapter 9, Maxwell's equations, but do you think that I mean we definitely shouldn't skip 6, but I guess like are 7 or 8 skippable, or like 10 or 11 definitely not worth missing. I can try and make the text bigger too. I guess like I can't see them all at once, but it's like we're just starting chapter 5 for the fields of moving charges. Then we're going to do that magnetic field. I assume we want to do induction. But then like AC currents are maybe not needed. 9 I definitely want to do. 8 is skippable, 7 is not. Okay. The 10 electric fields and matter and magnetic fields and matter. Be cool, but so maybe that'll be the plan. Like we'll go for 6, 7, and 9, and that can kind of be the goal for the reading group. Unless you're interested in some Femblocks or
No, whatever you want to do. Sounds good.
okay. 10, 11 are essential.
Actually, that chapter 8 might be stuff I know a little bit.
Yeah, I bet it's gonna be talking about. Well, yeah, it is just talking about circuits. So I bet you would know this.
I bet I would not know all of it, but I might know a
Yeah.
little bit of it.
Complex exponential solutions. Oh, right, because it's alternating current. We're just starting on chapter 5. So the rate we've been going with maybe like we have 3 more chapters to cover. That'll be like 2 or 3 more months, and then whether switch topics or take a break from the group or something. Um, 5, 6, 7, 9. Okay. Thank you, Cook. So for chapter 5, there are only 9 actual problems with solutions. There may be like 20 more exercises. But all the problems were there's one 1-star problem, and then the rest are 2-star. So I just kind of said let's do them all, or as many as we can. And there were 2 from the exercises that looked interesting. So I think just let's go down the line and start with 1 through 9. Something with the analogous chapter have this number blip. Ooh, okay, that's a good idea. Maxwell's equations. Okay. I should do I have somewhere I can write that down? And here's a random notepad text file that we'll forget to check. Okay. So, number one, on a nylon filament 0.01 centimeter in diameter and 4 centimeters long, there are 5.0 times 10 to the 8 extra electrons distributed uniformly over the surface. What is the electric field strength at the surface of the filament in the rest frame of the filament in a frame in which the filament is moving at a speed 0.9 c in a direction parallel to its length? Recommended University Physics, Young and Friedman. Oh, okay. Let's see if I can track down a copy of it. Hey, math channel. This is secretly the Riemann hypothesis. Trust me. Okay. Thank you, Cook. In the solutions? Oh, I mean, it would save me the trouble of looking for it, but it's no big deal either way. Ion filament. So this is what? Basically a very thin disk?
I think it's more like a piece of hair, isn't it?
Filament. Oh, you're right. Yeah. So I wonder if we can approximate it as a line of charge. Maybe that's going to go against the spirit of the problem, but. It is finite. Oh, yes, of Parcells. We only have the solutions that are provided in the book. If there's a separate solution book, we don't have that. Do they do it for the exercises too? That might be nice. I don't know if we need it, but we could get sigma. Oh, wow. Yeah, thank you, Cook. Surface area of a cylinder. I remember the two end caps or circles. 2 pi RH. So we have minus 5.0 times 10 to the 8 E. Pi R 2 pi RH 2 pi 0.005 times 4. Hey, Homo sapiens. Plus 2 pi 0.00, oops, 5 cm squared. I don't know if we need this sigma, but it just seems like it might be helpful. Field strength at the surface of the filament. This is only a 1 star, so I assume they don't want us to go too crazy here with doing some Coulomb's law or Gauss's law thing. Well, like, probably Gauss's law is fair game.
Yeah. I kind of like what you said about, approximated as a line of charge.
Yeah, I'm just wondering, they say just at the surface of the filament. So I'm wondering if we need to consider, like, what if we're at a point by, like, one of the end caps? Like, the approximation wouldn't work there. But if we were allowed to just choose a point, like, right there in the middle, then I do like the line of charge thing. Hmm. Should feel string at the surface of the filament. Okay, yeah, I feel like we should just do that line of charge thing, because I don't see what else we could possibly do here.
Well, we could do a little pill box, right, as they call it.
True.
And maybe
Like,
the pill box could be like a little disc right in the middle, right in the center, like a disc shape. But aren't we just basically, wasn't that just kind of deriving the formula for the field strength due to a line of charge?
I think it will be, yeah. So we could just cut straight to that.
What is
I
it?
assume
Do you
that's the
remember?
point. I was just gonna go and find it. The book is using a little bit in chapter 5, but
I think it's like lambda over 2 pi r.
it's something like that.
Yeah, I feel like I just saw it somewhere in this chapter when I was reading it this
Lambda
morning.
over 2 pi epsilon naught r.
Oh, epsilon naught. Yeah.
It's a large file. No worries, Cook. And I guess instead of, what do we want to call it, sigma? It doesn't matter if I call it sigma or lambda, my original thing for now. So they're asking at the surface of the filament, so maybe that's where we use this 0.01 centimeter measurement. Like that's going to be our R. If we imagine the line of charge is like just going through the middle of this thing.
Yeah, I would think so. Yeah.
So maybe I will rename my sigma to lambda. Oh wait, no, that wouldn't be lambda. Or that I would need to change the formula. If we're approximating this as a line, the lambda is going to be the total charge divided by the total length of this line.
Yeah. Can we forget about the end caps, or is that not fair?
I'm just forgetting about the end caps right now. I don't know if that's fair or not though. I'll explain the answer to this question. There is a solution in the back of the book for this one. We just don't want to look at it until we have to. Um, crunch some numbers. Minus 5.0. It's 10 to the 8 over 4 over 2 pi. Did you know there's so much math in physics? Oh, thunder. There is a whole world of multivariable calculus that goes on in this book especially. Like doing double and triple integrals, spherical coordinates, cylindrical coordinates. It's like calculus in 3 dimensions, Thunder. I guess you may haven't taken that class yet. Yeah, actually, I think that would technically count as multivariable calculus. How much math do I need to know to become a theoretical physicist? And the punchline? More? um, and now I'm going to charge E. It's 1.602. Ugh. 0.602 times 10 to the minus 19c over E, just to do the unit conversion. Minus 19. I guess we need to get into meters, so 4 meters is 0.04, or 4 centimeters is 0.04 meters. And, oh, I need my epsilon naught.
Well, you got centimeters that can cancel. No, sorry, they don't cancel, do they?
Oh, no, I guess they wouldn't.
No, they don't.
8.854 times 10 to the minus 12. I already forgot what I said.
Yeah.
It's 12. Okay, and then now it's point, I guess 3 zeros in a 1 meter. 1, 2, 3. And this should be in the proper units. Okay, so minus, we can call it 3.6 times 10 to the 5th. Coulombs. Oh, Wolfram knows epsilon naught?
Isn't
Massive
it,
sum.
wait,
Oh,
newtons per coulomb, right?
newtons per coulomb? Oh, you're right, yeah. I feel like I'm bad at actual calculations with numbers after reading this book and the units, since it's so like conceptual. Is there not a special unit for field? I guess not. Feels weird.
I always see it as newtons per coulomb or volts per meter.
Okay. Oh, that's right, yeah. Does this, it's not giving us the actual, oh wait, no, this is the answer that they're saying. That, I feel like there's an error, right? That doesn't look right. Oh, it is right. Yeah, times 10 to the 5th. Okay, nice. It's too complicated to ask why for a single slit diffraction the central maximum is double the width of the other maximum. I definitely don't know that offhand, so for now the answer is yes, it's too complicated. I could try and Google it after this, but yeah. Okay, so now it's gonna, for part B, we have a Lorentz contraction to deal with. So if it's,
Right. Yeah, I was just reading about this and the parallel and perpendicular components of the field.
Yeah.
And it had me confused because I was like, well, see, I was reading this question. I was thinking, well, it's coming out at right angles, so it should be the same. But no, it won't be the same, will it? This is the case where you actually have to do the contraction on it.
Oh yeah, I just assumed that this was the right direction for the Lorentz contraction. Otherwise, it wouldn't be as interesting a question as it could be. Oh, thank you, Cook. So if we're moving it, I think we need to get the Lorentz factor, whatever it is, and divide the total length by that. So I want to say that beta is V over C, which is just 0.9. And then gamma, the actual factor that we want, I think is 1 over root 1 minus beta squared.
Yep, I got it written down here. I'm looking at it.
Oh, nice. Flash Code, thank you for the follow. I should have kept that up. Okay, well, from alpha does do undo. Thank God. So I may need that calculation in a minute. 1 over square root 1 minus 0.9 squared. 2.29, we'll call it.
So that's gamma.
Right. So in this frame, it's going to be...
Now we either multiply or divide by gamma. Which one?
I expect it to be shorter. It's always the longest in its rest frame. I think that's a rule that they said at some point.
Is that what they said? I was thinking they said it was the shortest in the rest frame.
Okay, let's...
I'm probably wrong, Don. You know what? I'll pull it up.
I mean, this was a struggle, so... I'm looking at Appendix G right now.
The transverse component of the electric field is smaller in the frame of the sources than in any other frame. So wait, so that means the field is smaller in the rest frame, right?
Oh god, those rules were so like backwards. Like the field is smaller, but the force is bigger, and I was having a hard time keeping track of which is which. But it depends on the thing you're actually measuring. Sometimes it's longer, sometimes it's shorter.
Yeah. I'm looking at page 245.
245. I want to see if I can lengths between fixed points in F prime.
In the appendix, okay.
Yeah. To be shorter. Wait. Lengths between fixed points in F prime, if parallel to the relative velocity of the frames, are judged by observers in F to be shorter by the factor by observers in F. Shorter by the factor of 1 over gamma. Oh god. Do they write like an actual like separate rule here? No, they don't.
So if the length is shorter, then that means for a fixed means for a length of a uniform charge distribution, you sort of squish the charges together, right? So the sigma gets bigger.
Right, same charge, different length.
And so the field strength would get bigger, right, when it's moving.
Yeah, so I think what's going to happen is back to the Excalibur, this 4 centimeters should be something smaller, so it should get a stronger field. Is what my intuition is telling me.
Yeah, I think I agree with that. So we're going to multiply that original field by the gamma. Does that sound right?
Oh, you want to... Yeah, we can do that directly. Yeah, I want to see it both ways. I was going to take the same exact formula and do 4 divided by 2.29, but it should still work for multiplying the field by that factor. Is that the same thing that I'm doing here? Yeah, it is. Okay. So we could say, I guess, E prime is 2.29 times minus 3.6 times 10 to the 5th newtons per coulomb. What? So that's 8.2 times 10 to the fifth. And yeah, you're right. I think that should be like the only fact that we need. I was going back to like the actual thing, but I don't think we need that. Oh, so wait, actually, we could talk about the end
Yeah, what
caps
are those?
where. Oh, sorry, what?
I'm looking at the stream and you're looking at equation 530.
Yeah, and this is from
And
the chapter summary, so there, it should be somewhere earlier too. But sorry, go on.
yeah, okay. I was just wondering what those words were. Source and lab. I hadn't seen those. So
Oh, they use lab as like the rest frame of like. I guess to explain the source frame is the rest frame of the charge. So the first one we did, I'd say, is the source frame when it wasn't moving. But now we're the
yeah,
lab and we're seeing it moving to the right with 0.9c.
yeah. Yeah, so basically we just used that equation, right? 530.
Yeah, so we did the perpendicular one. But
Yeah.
at the end caps where it's parallel, I think I might have assumed the direction of movement. It would be the same though as from before.
Yeah, that's right. So you think we were supposed to pay attention to the end caps?
Um,
Mhm.
I still don't know how to do the actual calculation, but
I mean, let's just say whatever the field is at near the end caps, it's going to be the same
yeah,
for A and B. How about that?
it's moving parallel to its length. Yeah, so are you okay to look at the answer?
Yeah, I think we're probably,
So I think it's
I
like
think we've
sufficient.
probably done what we were supposed to do.
Yeah.
I'm hoping this won't be the only question I understand today.
Wait, 2 times 10 to the minus. Oh, that's for lambda. 7.2 times 10 to the fifth. We didn't get that. We got 3.6. We got half.
7? Oh, we're out by half, are we?
Did I make an entry error? Two pi epsilon naught. Why are differential equations in waves? Oh, just you wait, Thunder. It'll get worse. Depending how far you go, at least. Um, 5 times 10 to the 8th times 1.6. That's 19th. That's fine. The linear charge density is that, which I have. 5 times 10 to the minus 5. Why do I have a 1? Oh, I put in the diameter. That's why I'm off by a factor of 2. We need the radius in that equation.
Oh,
Wait.
I thought
No,
I
I'm
thought
down
you had a
by...
5
That's
there.
wrong.
I thought you'd had a 5 there.
Uh... I had 0.0001. But this is still wrong. It's going the wrong direction. I'm down by a quarter now on my thing. I mean, okay, well, I'm glad they also use the same approximation that it's just for like an infinite line. They don't even talk about the end caps. But
Oh, 0.01 centimeters was the diameter. Oh, I see. I hadn't realized that. I thought that was the radius. Had misread the question.
oh yeah,
Okay,
but
so
even then, if I cut the radius that I had in half, it's it's going the wrong direction. We're now out by a quarter rather than a half.
Yeah, well,
Ooh.
didn't we use, I mean, we used that a couple times in our calculations.
Did we?
I
I mean,
thought
it's gonna mess
so.
up our answer to part B as well, but thank you for the recommendation there, Cook. Because once this group is over, I don't know what I'm gonna do with it, but or once like this topic is over, I don't know what'll come, but it's good to have that in mind. Um, 7.2 times 10 to the fifth. Okay, let me just enter in the exact thing that they did and see if I get. I wonder if there's like a typo in the 2 times 10 to the, is it minus 9? Yep. Over 2 pi what am I looking at? 8.85 times 10 to the minus 12. Times 5 times 10 to the minus 5. Chapter 8 of that book would be a really good supplement for self-streaming of E&M waves. Ooh, okay. Because that does give me the same thing as what the book got. So let's break it down into parts. Oh, wait, no. 2 times... Wait. Is my conversion factor wrong? No? Okay, I get
Where?
the same value of lambda as they get in coulombs per meter. How is this possible? It must be the radius. Five times 10 to the minus 5. Oh, I saw the 2.29 thing. Oops. Okay, that gets the right answer. I think it was just the radius, and I forgot that I had the Lorentz constant on there from part B. Charge of electron? Ooh, okay. I was gonna put E, but I didn't think Wolfram would interpret it right, so I was like, yeah, let's just type it out. Okay, so the issue was I need to make that one into an O5, and that gets us the right answer, but that's a mistake that I can live with.
Yeah.
And then for the next one, we're still multiplying by 2.29. So that bumps it up to 1.6 times 10 to the 6. I haven't checked if that's right yet, but... Worth trying out, because then you can double check your answers with the units. Okay, we do get the same answer for part B, the rate Lorentz constant. They didn't even talk about the end caps, so because we didn't need to do that, but really worth trying out. Oh, okay. Charge of the electron. Yeah, because I didn't know Wolfram Alpha handled units, so I was just kind of avoiding it. How would I don't know how I would know that conversion factor, like or coulombs per charge of electron. 0.04 meters. Meters. Unit handling is one of its best features.
Electric field strength.
Okay,
Cool.
cool. That is nice. Because kilogram meters per second squared is newtons, and then I assume a second times an ampere is equivalent.
Coulomb,
That feels
yeah.
right. Yeah.
Yeah, because amperes are coulombs per second.
Right. Okay. I mean, how would I tell Wolfram Alpha to do it in to give me the units that I want though? For the result. That's wasn't sure because I didn't want to give it to me in like centimeters per whatever. It's not quite right. Really? Oh, in blah. So I could have given it the original thing. You're saying? Oh, okay, okay. Uh,
That was number of electrons.
yeah, it's supposed to go with the E up there. Wolfram Alpha is just formatting it weird, but it is the E that's right there. So actually, okay, if we're gonna really limit test this, let's get rid of this conversion factor for coulombs or for charge electron to coulombs. In newtons per coulomb. I might need to type out the units. Assuming Celsius? Nope. Don't assume Celsius.
Newtons per Celsius.
Odd. If I change it to natural language. Nope. Not converting. I don't know. I'm sure there's a way to make Wolfram Alpha figure that out, but I don't know. 5 times 10 to the minus 3 cm. I changed it to that just to like try out that conversion thing, but we need to group up with their value. How about I just don't try to... Okay, Wolfram Alpha just converts it to the electric field strength units anyway. That's the link though if you want it, but I guess I just, you don't need to add on the end thing. At least I was worried about nothing. Okay, that's good to know. All right, so also, hey Milk. Number 2. Probably take these screenshots a little bigger than I have to. Okay. Maximum horizontal force. A charge Q1 is at rest at the origin, and a charge Q2 moves with speed beta c in the x direction along the line z equals b. At what angle theta, shown in figure 5.27, would the horizontal component of the force on Q1 be maximum? Horizontal component? A charge Q1 is at rest at the origin, charge Q2 moves beta c in the x direction. For what angle theta shown the horizontal component of the force on Q1 be maximum?
Okay, how about equation 531? in that chapter summary.
Ah, that looks like a good thing to use here. And a little more complicated than I feel like writing out an Excel draw right now. So let's get a screenshot. So now we only care about the horizontal component.
Yeah. Actually, I was going to ask you, Don, I don't know, because I mean, I'm way behind in this chapter. And I just was trying to read this equation 531 a little bit before we came on. And I hadn't gotten far enough to work out what the angle theta represented in this equation. Like what angle is that talking about?
It should be the angle, the same as the angle that they draw in that figure. Where do they derive this? So on page 248 is where the equation that you pointed out comes from. It's the angle between the velocity of the frame and the point at which you're measuring it, I think. So basically from the x-axis to the point.
The x-axis and the x prime axis are in the same direction. Theta prime. Theta prime, the angle between the direction of motion of the charge and the radius vector from the instantaneous position of the charge to the point of observation.
Yeah.
So who's observing it? So we're observing that charge from the origin right now, right, in our problem.
Right. We're more or less at Q1 and we're staying still while Q2 is moving. From our perspective.
So it's theta prime, and can we just say theta prime and theta are the same angle?
No, because if we were on
I don't think that's true, is
Q2,
it?
yeah, it's going to be different.
Yeah. Yeah, I'm trying to work out which angle we're talking about here. Because I remember reading, I just read this equation a couple of minutes ago, and I was like, what angle are they talking about here?
Yeah. I guess here they're measuring theta from the negative x-axis. Now, the thing that's making me curious is that the next equation down in that chapter summary points out that if you're parallel to the velocity, the force is actually the same. You only need the Lorentz factor if you're talking about perpendicular force to the motion. Which makes me think we could take this equation for E, multiply in Q2, and then we take a derivative somewhere, I guess with respect to theta. But is this this is like the total field? Or that's even just the magnitude.
The radial magnitude, yeah.
The quick explanation, Thunder, is that when you're talking about a special relativity, as far as I know, if you're watching someone who's moving and they have like just say a rod, if they hold the rod, I think parallel to the direction they're moving, it's going to look shorter to you than it does to them. But if they hold the rod perpendicular to the way they're moving, the rod looks the same length. And if they're holding it parallel, then that's shorter by a factor of 1 over gamma. That's kind of like the idea behind what the Lorentz factor is about. Yeah, it's kind of mind-blowing to me too. Oh, okay. Thank you, Cook. And so if you have like just say like a line of charge, the amount of charge is the same, but if that's moving, the same amount of charge is going to get compressed into a smaller area, and that's what causes apparently magnetism. But we haven't gotten that far yet. Or it is somehow related to magnetism. Uh oh wait, is there a separate equation for force? I should check that. Um I think we can still simply multiply QE. Ooh. Type in the value of the constants either. Yeah, that's true, Cook. Okay, so I I think we only care about the parallel force here. And that's the same in each frame. So I think we can simply say Q1, Q2 over 4 pi epsilon naught R. I mean, isn't this... This seems like they're asking the simpler version of the question. Because we could also have done this chapter, or this question in chapter 1, if there is no change between the frames. I mean, I guess maybe... I guess we have to worry about the betas. That's a terrible derivative to take. Hmm.
You're thinking we got to differentiate with respect to theta now?
That's where I was going with this. I guess R is dependent on theta too, though. I don't feel all that confident in this though. Wait, I didn't do that right. Uh, cosine theta is equal to x over r. So it should be x divided by cosine squared if I want to get r.
We don't know X, but we know Z. So you could use Z equals B.
True. Yeah, yeah, okay. Yeah. So we want b over sine theta? Sine theta is equal to b over r. Yeah. That makes the derivative even worse to take though.
Hmm.
So we could like shuffle some things around to at least keep the constants out of the way. B squared. But this derivative does not look fun. So it's making me think that this is the wrong track, or they're just going to say to use a computer program.
It's only question 2. They're going to hit us with a computer program already?
Hey, Joseph. Feels a nice sleep during the day and weekend sleep now, crane later. Nice, nice. Uh, we want to take the derivative of this thing with respect to theta cook and know where it equals 0. We're trying to maximize theta, or trying to maximize the force with respect to theta. I just feel like if we have something this complicated, that we're probably on the wrong track. Yeah, we can see what it comes up with, I guess. What would be the answer if relativity wasn't in the picture? Oh, you know, it's actually difficult to answer because we're looking at it at a snapshot in time, but the actual path of this particle is going to be some crazy curve. Like it's going to curve, they're going to repel each other. It's not just going to forever move in a straight line without an outside force compensating at least.
Oh, well, I think in the question, we're supposed to assume that there would be some kind of compensating way to keep it on that line.
Okay.
Because it does say,
Oh,
along
true.
the line.
Yeah. I guess doing this by hand might not be so bad because we don't have to worry about the denominator. when it's being equal to 0. But if Wolfram Alpha can do it, that's still all the better. Shift the view up a little bit. Sounds good, Thunder. We'll probably try to do this one problem and then maybe another, depending on the time.
I will say this chapter has been, from what I've read of it so far, I think it's the most interesting chapter. At least to me, it was like all this new stuff that I had never seen before.
Yeah, it's there's been a couple of spots where I'm just like, why? Like, I love those chapters so much. What? I don't know if you got to the part where they explain.
Yeah,
where
I'm only halfway through it.
Okay. So yeah, you haven't seen it yet then. Where is it? You get these super
Yeah,
crazy. Sorry, what?
this formula we're looking at right now is right about where I got up to.
Oh shoot, I turned away from it. Okay, this. Like where an electromagnetic wave comes from because of relativity, and you get these crazy looking fields. This is the part that really like got me. Yeah, Thunder. Like,
Oh,
yeah,
that's like the
I'm getting
front
really
cover
interested
of
in
the
it.
textbook.
Oh, is it?
I think so. The front cover, it looks like that. Something like that.
Oh, it does. Yeah, it's the same thing. But yeah, Thunder. It's because if the normal electric field of a particle that's stationary, you know, with the field lines just looks like that, and then one that's in motion looks, oops, more like this, where it kind of bunches up at the top and bottom. If you transition from, if you have an acceleration, like you're going from stationary to being in motion, there's this like transition that happens where there's like a shell where it's normal because it can only update as fast as the speed of light. And so that the information that the particle is changing its velocity has to like propagate, and that's where you get this like difference in the field where there's a shell where it's normal, and then the outside shell is more like, I'm drawing it terribly, but yeah, that's what makes the shell. It's basically like the speed of light being a limit to how fast this field can update. And I thought that was super cool. Spins out the cooling force obeys relativity. If one charge is moved, it takes a while. There's a kink in the E field to reach the second charge. So the cooling force, the second charge field doesn't instantly change. Yeah. There's 12 pounds of cocaine to even begin to understand what's going on. Basically, if a charge is staying still as a different field versus when it's in motion, and if it goes from being still to moving, it takes a certain amount of time for the actual field to update from one to the other. And like it's like a shell that expands around as like things get updated as time goes on. Did I copy the wrong? I think I must have copied. Did I even paste the link from Cook? I didn't. Wow, pi n? Or oh, we get a couple of solutions. Is that the case, Cook? I thought they detected like a Lido or whatever. They detected a gravitational wave, right? Or you're just saying that Newton's law doesn't work with relativity, it has to be updated by relativity. Sorry, Finlux, for the little like non sequitur, but
No, you're good.
to the equivalence principle and general relativity. Oh, okay. So this is what Wolfram Alpha gets for when the derivative with respect to theta becomes 0. B is beta here. I don't like that we get this weird arc cosine thing. Oh, even Newton noticed that. Okay. Well, I guess, okay, theta equals pi doesn't make sense. Where's the component? The constants stay the same. And then get rid of these. Oh, it doesn't actually show us. We could. I want to see the actual derivative. I'm just a little bit nervous about these like weird arc cosines. Oops. Oh God. Okay, why we didn't do that by hand? Um. Are these actual like distinct answers here? I guess they are. Beta squared plus 1 over beta squared minus 3. Or, oops, it's the same thing but plus pi. Wait. Okay, yeah. So if it's a pebble in Alpha Centauri that shifts a bit, how could it be the gravitational force that exerts over here instantly updates? I mean, I wouldn't see why not if I hadn't heard of relativity, I guess. I was hoping we get a cleaner answer here that doesn't depend on beta. Does that make sense? I guess it has to depend on beta because of the second question they ask.
Yeah, it makes sense that beta would show up.
Okay. Oh, I guess, yeah, that does change how the field looks, the value of beta. So I guess if we just take these as a fact, we have to consider beta is about 1 and beta is about 0. Are these... These should really be most of the same angle, right? Or if we have plus pi, we're over in quadrant 4 or something, like we're positive x and negative y, which we don't, I think we only want the first one. The more I think about it, the more the second one doesn't make sense for our context. Because this one is over in like the negative y's, I think. Or measuring theta.
Hmm.
Oh wait, we're considering it. What is theta? Okay, yeah, we have to consider theta here. This is 2 over negative 2. Oh, this is 0, isn't it? Because arc cosine of negative 1 is pi?
Pi. Okay.
Uh, and that means it'll be
Wasn't there a
going
one
exactly
half?
at the speed of light. Oh, what?
Wasn't there a factor of 1/2 in the Wolfram alpha solutions?
Oh. Oh, you're right. Thank you. Hey, Dramagnopite. Or Dram. I think that's what you go by. Good catch, Femlux. 1/2. Anything works, sounds good. One half. Oh, so maybe that throws a wrench into. Oh no, it's still on that first one, I think. So then that means we get pi over 2 then.
And that second solution had a inverse cosine as well.
Oh yeah. I was there in my head, but I forgot to write it. Nail the full version? Oh, good. So kind of seen as physically reasonable. Oh, that's interesting to know, Cook. So if beta is about 1, that means it's pretty much traveling at the speed of light.
Yeah.
And the force is maximized when they're directly in a line with each other, like perpendicular. Does that make sense?
You know, maybe that does make sense, because you remember the pictures they showed in the chapter where they had sort of different things moving right, electrons moving to the right, and one of them was like 30% of the speed of light, and then they redid it at 80% of the speed of light, and they showed the
Oh
field
yeah.
strength. And as that beta got closer and closer to 1, it seemed like the fields were getting sort of compressed on the vertical. Yeah, those ones.
What was that one? I think that was just like the same beta but with different times. Okay, yeah, this is beta equals 0.8.
Yeah, the second one was 0.8, and the one before that was like 0.3.
Yeah.
And so I
okay.
assume if you take it all the way up to 1, it might just be like infinite. It might just be fields going vertically.
Oh yeah. Okay. I can see that then.
Wait a sec, what's Dr. Cook saying in chat?
I think it's about Newton's law of gravity as written, not accounting for relativity. This is a quote from Newton. So you can see that inanimate matter should, without the mediation of something else which is not material, operate upon and affect other matter without mutual contact. That gravity should be innate, inherent, and essential to matter. So that one body may act upon each other at a distance through a vacuum without the mediation of anything else by and wow, this is a lot of words. To me, a great absurdity. It's saying that there needs to be some mechanism for these forces to actually happen. That I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. Gravity must be caused by an agent acting constantly according to certain laws. This agent being material or immaterial, I have left to consideration of my readers. Oh my god, classic. By principle of vocabulary, which is something different than relativity. Oh, okay. Yeah, because I'm getting kind of like quantum mechanics vibes from that statement, or like the actual like packets of the force. I think that's what quantum mechanics deals with, maybe.
I saw a formula in this chapter that reminded me of quantum mechanics. It was
Oh,
something to
which
do with
one?
the energy of the moving particle in terms of like the mass and the momentum. And it
Oh
was something
yeah.
like m squared times c to the fourth equals e squared plus p squared c v squared or something. I forget what it was, but it was, and I was like, oh, that's one of the formulas I remember seeing when I was trying to learn quantum mechanics, and I didn't really understand where it came from. I'm sure it was more relativity stuff.
um, at least in the appendix, they have like momentum is gamma m0u, and
Hmm.
energy is gamma m0c squared. Um,
You know what was cool? They said that charge is a scalar, and
right.
so it was invariant under the transformations.
Yeah. Actually, yeah, it's an interesting thing. Like, so you could express position as a vector, and that does get affected.
When they're talking about four vectors, are they just saying like x, y, z, and t? Is that what they mean by a four vector?
Yeah, space time.
Okay.
So maybe these answers are okay since we seem to be getting reasonable seeming answers for betas about one. If this thing is not moving, we should expect it to be whatever the normal Coulomb's law answer give us in electrostatics, I think. Which I don't know what that would be offhand, but inverse cosine of minus a third. Well, that's not a unit circle, was it? A third wouldn't be, so that's we need.
Didn't we solve this problem in chapter one?
Did we? We
I don't
probably.
know. I don't know. It feels like a problem we would have solved in chapter one.
Yeah, there's a chapter one problem in here somewhere.
1.23 radians.
Yeah.
What is that? Like
Uh,
60, 70 degrees or something?
somewhere around pi over 3, I assume. Oh my god. In degrees. 70.53. Oh, right. Negative 30 degrees. No, that's not right either, but 70.53, really? Oh, yeah, yeah, yeah. Okay. If it's around pi over 3, it'd be around 70. Okay. Let's see if that.
It makes sense. It makes sense there's going to be a sweet spot, right? Because if you try, you want it to be closer to have a higher, field strength magnitude, but if the closest you can get it, it's going to be pushing it vertically downward and it won't be pushing it horizontally at all. So there'll be some
Yeah.
sweet spot. 70 degrees sounds maybe okay.
Yeah, because it is. I wouldn't be like 45 degrees or something because it's too far away.
Right.
But I could see that at least. I'm going to the answer.
Hey,
Oh,
wait a
almost.
second. Before you go
Yep.
before you go to the answer, I just realized I have a question.
Mhm.
We had two different B's in our problem, and one of them was the beta for the ratio of the speed of light, right? The percentage of the speed of light. But the other one was the B was the distance from the X
Yeah.
to the line. So did we keep track of that B somewhere? We didn't get our B. What I'm saying is we didn't get the B mixed up with the beta, did we?
Uh, we did not get it mixed up. The beta that was. Oops, I don't have that anymore.
I see it. It's in the denominator out the front there. Okay.
Um.
Sorry, Don.
Oh,
I
no
got confused there
worries.
for a
It
second.
is interesting that it doesn't depend on B though. Like that seems
Yeah,
weird.
isn't that does seem kind of weird. That does seem kind of weird. It seems if beta is 0, then it seems the answer would be a function of B, doesn't it?
Yeah, I
Maybe
would
not.
expect the height to be important here. Evidently not. Hmm.
All right. Well, did we finish it? Let's see.
Let's see. Magnitude electric fields given by 5.15. I think it might be the same one that we grabbed. Factor of cosine theta, sine squared cosine theta. Oh, hey, okay, we have the
Wow,
same
you got
thing.
it. Yeah, you got it perfectly.
Simplifying. Well, yeah, they don't even say to use a computer program here. They just do
Well,
it.
I was looking at it and thinking we could change that sine squared into cosine squared, and I didn't know if that would help us.
Oh, I guess it would, yeah. A little bit. We still have to take derivative of the denominator, though, for quotient rule. Um,
So, did we get
ooh.
this last part wrong?
Wait, if beta is 1, we get 90 degrees, but this does not... Well, cosine... That does not look the same thing, but I wonder if it secretly is.
Oh, are we missing a square root? We got 1/3. Arc cos of a third.
The Wolfram
Ah,
alpha.
we forgot the one. We forgot the 1/2, right? There's a 1/2 arc cosine of a third.
Oh, shoot. I forgot the 1/2, but yeah. Thank you for being kind.
Well,
Um,
you're doing all the work. I'm just sitting here, so
2.18
you're welcome.
radians. Let me get that in degrees again. I don't know why I'm getting in radians. It's not really that helpful here. 125 degrees.
Yeah, that's too big, right?
I mean, relative to the 125. Oh, that's on the right side with our measuring theta. Huh. So maybe. We still got the right answer for beta equals 1, though. I wonder if that was a
Yeah.
coincidence or if we just got a different looking thing that's still the same. Oh, wait.
Well,
Yeah,
no,
for
I
beta,
think
it's about zeros, right?
yeah, I mean, the function you came up with was correct, right? I mean, they showed that in the answers. Sine squared times cosine over 1 minus beta squared sine squared to the 3/2. Yeah, proportional to that. That's exactly what you had.
And there, no, yeah, over the smallness of the cosine. Okay, yeah. If theta equals 90 exactly, the horizontal force is 0. Interesting. Because they are directly over each other, I guess. If beta is about 0, then sine of theta is about √2/3. Completely check from scratch, this is the correct result in the non-relativistic case. Or we're looking at one of the forces proportional to sine squared cosine theta. So they did it a different way, but we once we fix my typos, we get the same answer.
You know what? If you don't add pi to that, you get the 54 degrees that I think they came up with. Yeah. So
Oh, there's 2 points where it happens, yeah. Because it should happen symmetrically on the left and right sides. That seems reasonable, right? Like an angle of 54.7 measured from the negative or the positive x-axis, because symmetry, probably.
yeah.
Dram says, I was curious about viewing things as 4D. Do we view it as a way of mathematically plotting relativity, or do we view it as literally 4D shape with the rest of the 4D axis being essentially behind every point? Ooh, I definitely don't know enough about that to say. I imagine it's more of like a mathematical like convenience thing, just have it all in one vector and they all undergo similar transformations. I don't imagine you'd actually try to visualize it four dimensionally. Like what the book does is it'll show one like two or three dimensional plot for space, followed by a separate one showing a different point in time. Okay, that was a neat problem. See, about like 15 minutes left. What does the next one look like? If we're really smart, we might be able to get this in not too much time.
Yep.
Let's see. Comes from the fact that PP is a Lorentz invariant? P dot P? Oh, momentum dot momentum. Okay.
Yeah,
Wait.
that's the equation. That's exactly, yeah, that's the
Okay.
one. PC squared plus MC squared, the whole thing squared. Yeah, that was on my equation sheet for the first exam in quantum mechanics.
Oh.
That was a hell of an equation sheet. I've still got that around somewhere. That thing was full of cool equations. It really was.
I bet.
Everything was in terms of that Planck constant.
Oh, cool. PC. Huh. That's cool, Cook. Okay, so Newton's third law. In laboratory frame, protons at rest at the origin t equals 0.
That's right.
At that instant, a negative pion charge minus e has been traveling along the x at speed of 0.6 c, reaches the point x equals 0.01 centimeter. There are no other charges around. What is the magnitude of the force on the pion? Oh, we have proton at rest, and then a negative pion enters the scene. Magnitude of the force on the pion. Oh, Newton's third law. Okay. Then my CH, I give up in knowing how it was derived. I remember learning it once. I don't remember it though.
Yeah, I learned about it. I don't remember.
Is it like the
Don't
or like
remember.
is
I
it the
think it,
H
you
bar
know what?
thing?
I think it came from the photoelectric effect, if I'm not wrong. I think it was that
Hmm.
photoelectric effect, and that's how they came up with quantizing the energy of a ray of light, right, or a photon, right?
Oh, yeah, I hardly remember it.
Yeah, exactly. Some guy was like, "Let's shine the UV light at the metal and see what happens." Crazy.
So is I think our pion is to the right of the charge and moving, right? As far as I'm reading this problem.
Oh, that's right. We're doing a problem.
Oh no worries. Yeah. I don't know if we're gonna be able to do it in time, but I was wondering if we could like squeeze it in.
Yeah, let's take a look at it.
Anything to solve the ultraviolet catastrophe. Ooh.
This feels like, I don't know. I mean, looking at this question, it looks like it's easier than the last one we did, doesn't it? I don't know.
I mean, it's kind of a weird thing where it seems like if the charge they're kind of ignoring like what happens when the two charges touch, I guess, but I assume we just ignore that. It does seem like a straight calculation. Oh, what's gonna happen? They're because they're asking the magnitude of the force on the pion, then the magnitude of the force on the proton. Uh, and Deco Prince, if I'm saying the right. Thank you for the follow. Um,
Wait, I think you got the green vector going the wrong way, isn't it?
is it? That's what I was
Well, I don't
trying to
know.
figure out. They said just a speed of point. It's probably one of these at a speed of 0.6 c. So they don't even say the direction. I guess
Traveling
it doesn't
in
matter
along
for
the
relativity though, does
x-axis.
it? Huh.
Ah, that's a good. Well, yeah, maybe you're right. Or doesn't it matter? It doesn't matter which way it's going. Just the magnitude of that relative velocity.
I guess so. As weird as that feels. So we can use that, I think the same two equations as the last one.
Yeah.
Um, well, I
And
guess,
theta has to equal 0, doesn't it?
yeah,
That
we don't
seems
have any
nice.
perpendicular force. So why aren't they making us do more relativity? That's kind of weird. They should have equal forces, I think. They'd have different forces if we had perpendicular force. Uh, if theta equals 0, what happens to this equation for E? Sine of the 0 is 0. So we just have a 1 minus
Yeah.
beta squared factor stuck on. Um, so I guess we're making the claim that these forces are equal. They do have opposite charge. I guess they'll have different directions, but they're asking about the magnitude anyway. This is weird. Now, the R we don't have to cut in half here. Or we can just use the 0.01 face value. And beta is 0.6. Question you use Coombs law. Second question you need to calculate field. So there is a relativistic effect. The magnitude of the force on the pion, which is the charge I put in green. What is the magnitude of the force on the proton? So this is because we're in our lab frame has the proton at rest. So the field from the proton is the same. So that's why we can use Coulomb's law on the pion. Which almost feels backwards, but I think it's what we do. But because this pion is moving, its field is all janky. So it's putting less of a force on the proton. Like its field is going to point like more up than to the side.
Oh,
I think that's what Cook is
all right.
saying. So this thing that I wrote here,
Yeah, they did say that at the start of the chapter, right? I mean, obviously, if they're both at rest, you just use Coulomb's law. But if one of them's moving and the other one's at rest, does it? You can still get away with Coulomb's law the one way, but not the other way. I had a feeling as soon as either one of them was moving, that Coulomb's law was off the table. But I guess not.
I think it's because in our frame of reference, the proton has a completely normal electric field. So any force from that thing is going to be our normal Coulomb's law. So on this thing here, or like on the other thing, we only care about the field of the proton. But then if we want the opposite direction, we only care about the field of the pion, and that field is different.
Okay.
I think that's what we're doing.
Got you.
Yeah. And so this thing that I wrote down here was the second scenario for the pion on the proton. Proton on pion will be the same thing without that 1 minus beta squared. Okay, might have just like put the answer to that third part there, but I'll read it in a second. Minus, oops, charge of electron squared over 4 pi permittivity of free space times 0.01 centimeter squared. Hopefully Wolfram Alpha understands this. Force, good. This is a very small force. I guess that's okay. Minus 2.3 times 10 to the minus 20 newtons.
Is it supposed to be 1 minus 0.6 whole thing squared, or is it the square supposed to be inside those parentheses?
It's inside. Thank you for pointing that out.
I'm just here to be a nitpicker, that's all.
That's a good nit to pick. It's 1.48. So the same order of magnitude? Yeah.
It's only 64% of the force.
Right. Yeah. Yeah, so that looks about right. What is a... Okay, so Newton's third law is every force has an equal and opposite force, right? Or every action has an equal and opposite reaction.
Yeah.
And here they don't appear to be equal. They should be opposite. Or yeah, they are opposite, but they're not equal. And they said this one is getting a little hot on the still, so that's probably like a hidden like 3 or 4 star problem to actually figure it out. But they're, and I think Cook put the answer in chat, but I'm trying not to look at it for another second until I think about it.
Well, I guess, you know, when you're moving at 0.6 of the speed of light, you can't trust Newton, right? That's the.
That could be it, yeah. Just doesn't work. And I don't think there would be anything special if we considered the other reference frame where the pion is at rest and the proton is in motion. Like we would still get unequal forces. Unless you somehow add those two things together, then I could see that equaling out. I don't know. I think I'm gonna look at what Cook is typing unless you have anything else to say.
No, nope. I'm glad I hung on as long as I did.
Okay. uh,
I did not come in today thinking I would understand 3 questions, but I feel like I more or less did.
hey, that's good.
Yeah, that's a win.
Yeah, especially with this book. Okay, so starting with the top of what Cook, actually, Dr. L. Yeah, this book is getting into relativity. So we just found the forces are, if you consider relativity, they aren't equal. And we're learning about Newton's third law here. So Dr. Cook's been typing up some stuff. The forces will be different, so the two charges will accelerate differently in the proton's rest frame, and the net momentum of the two particles will change. How can this be? Does it violate conservation of momentum? No, because there is a third object carrying momentum that keeps the total momentum conserved. I have no idea how to say that name, but thank you for the follow.
Longsword.
Wait, what?
It looked like longsword when I saw it on screen.
Okay, are you able to actually like read those characters?
It came up longsword with a number, I think.
Oh,
I don't
okay.
know.
In my activity feed, I just see non-English characters that I don't know what language it is, but I sure can't read it.
Oh, yeah.
So there's a third object carrying momentum that keeps the total momentum conserved. This missing momentum is carried by the electromagnetic field, which transmits the Coulomb force between the particles. The field itself has momentum. Somehow. The Lorentz force law, F equals Q times E plus V cross B to the to calculate the force on the moving negative pion. Since B equals 0, you just get F on pion equals Q sub pion times E created by proton. It's a Coulomb's law equation, V sub 2E created by pion. Or proton. It's really just statement of momentum conservation. I don't remember what Cook was saying yes to, but F equals dp over dt, so 0 equals F12 plus F21 equals d over dt, p1 plus p2 equals dp subtotal plus d, or over dt. Equal opposite forces between pairs if and only if total momentum of all pairs will remain constant. So conservation of momentum is the same as equal and opposite forces. Oh, and then there's an equal opposite force between pairs if and only if total momentum of all particles will remain constant. More important principle is conservation of momentum. In more general theories than Newtonian mechanics, such as Maxwell's E&M, we drop Newton's third law. An opposite force between objects, how can we even use this for fields? For its generalization, momentum is conserved. Okay, so the conservation of momentum implies both ways that Newton's third law, or they're equivalent. How can a field have mass? Like I'm thinking of P equals mv, just like the simple equation for momentum. Is that asking a question I don't want the answer to?
I bet you Planck's constant's going to come in.
The field has no mass, so we get E equals PC. Oh. So the momentum is energy over the speed of light. Light definitely carries energy. So the light carries momentum P. Oh, okay. I feel like a class in relativity or whatever should come with like a Tylenol for each class to deal with the headache.
A Tylenol and a bottle of gin.
Yeah. Huh.
Well, good stuff.
Yeah, I guess I'm gonna check the calculations here, but
Oh yeah,
we
let's see
definitely got
if
the
they
idea.
let's see what their answer was.
Force in the pion is 2.3 times 10 to the minus 20.
Yep, that's
Good.
what you got.
Um, 0.64 or whatever we just got, so 1.47 times 10 to the minus 20. Okay.
Yep.
So Newton's third law does not hold. The total momentum is conserved. Oh, wait. So Newton's third law is not the same thing as conservation of momentum for total. I guess.
We will learn in chapter 9 that there is momentum in the field, and the field is changing here. This is not a two-body system. Oh. Yeah, very cool. That's very, very cool.
Oh, Newton's
Yeah,
third law applies to the charges
this
does not
chapter is
hold.
something else.
It does hold if you include the field as the third body. I assume. Okay. Sorry, what?
I'm just saying this. I'm just marveling at this chapter. It's cool.
Yeah, I think I just like physics now. I used to say that I don't like it, but this is just cool. Okay. I guess we'll wrap up the group here then.
Yep, that's
For
a
this
good place
week.
to stop.
Thanks for being here for another session.
Well, thanks for
So-
carrying the day, Don. I was just there for moral support this time.
I appreciate it. I'm thinking only one more meeting on chapter 5 because it's kind of like foundational, I think, for the next one. So I think one more
Okay.
meeting on chapter 5, and then the week after that we'll do chapter 6, unless you want some more time, which is cool too.
Well, we'll see. I mean, next week we might fall in love with chapter 5 even more, and we'll just want to stay in it. So
That's
let's
true.
see what
Yeah,
happens.
we can do that too. But all right. Thanks. I'll see you.
Yep. Thanks.
Okay. Before I forget, let me export this thing. Yeah, this whole E&M thing has been so much fun, and Dr. Cook's help has been really nice. Need to go to quantum to violate the third law, it seems. I guess not, yeah. Alright, so I've got to stop in an hour, or like a little less than an hour, because I'm gonna see a movie tonight with some friends. But we have some questions from Thunder and maybe from Critical, so we can try and do those in the meantime here. Let me switch over my Twitch title and category. Answering math questions from chat and studying. Math. Dang it, and my category switch never takes on the first try. That's great, and there we go. Should get some music going too. Oh, you're not max volume, right? Good. Let's update this thing. Ah, almost there. Seeing how the sausage is made here. Is that even the expression? I don't think it is. Okay. Okay, and I did post the Excalibur route. Now, I didn't set up my whiteboard again because I was lazy again. But I'm just gonna use paint. Okay, let me catch up with the chat. No, I'm switched over. An electron and a positron, two particle pairs can each other to produce a photon. Right. If you watch this happen in a frame where the electron and positron are moving to the right, the net momentum before the annihilation is to the right. Resulting light must also carry momentum to the right. In that frame, I assume. I don't know. Newtonian mechanics. Equal and opposite force between all pairs of particles in a swarm of particles implies total momentum of the swarm of particles cannot change. We now emit fields into our ontology, emission of particles. How can we extend Newton's third law to fields? The answer is to replace force characterizations of total momentum as conserved characterization. So I'd phrase it this way. I gotta put emphasis. No, I feel that way too, Fembucks. Newton's third law is generalized to the conservation of momentum when we go to a field theory like Maxwell's E&M. Okay. Force between two fields wouldn't make sense anyway. But fields carry momentum, so it does make sense to speak of the total momentum, all particles in all fields being conserved. Indeed is what happens in E&M. When particles will falsely look like the momentum has not been conserved. That's kind of crazy. I guess we're going to talk about that more in chapter 9. Okay, so... And I say, like, I've been researching grad schools, and like I've been enjoying this so much that I've been researching for masters in applied math, but I'm actually researching for masters in physics too, because I'm not optimistic that like if they did let me in, it definitely they'd make me take some undergrad courses, which I think I would want. But this has been just so freaking like cool. So yeah, the general plan, we want to do 6, 7, and 9. And I think for the sake of the reading group, we might just like call it there. Like I'd probably still read 8, 10, and 11 because I have just enjoyed this so much. But I think the reading group should end like sooner rather than later, just because like it'd be nice to do something where more people are going to get involved if they can. I've kind of been debating that because you can see it from the book cover pic. The kink in the field carries the momentum from one particle to the other. Oh, really? That's what this does? Oh yeah, I want to keep this page open. Let me just favorite it. So yeah, once this reading group does end, I don't know if I'm gonna try to do another one immediately. I started the group because at the time there was a lot of pure math stuff happening on Twitch, and I wanted to do something else applied, but that's not really the same. Like Penn Center's doing physics reading group too, so I don't know if I want to continue doing physics. I think Mary's doing a linear algebra one. So if I did do something, I don't know what it would be that would be that unique, but anyway, so this is a question that Thunder sent me. Answer is A, I don't know why. Ah, Suna! Oh no. just zoomed out when I didn't mean to. Thank you very much for the raid. How's it going? How's your stream? Better incident of the same angle theta. On the core cladding boundary of optical fibers P and Q. What the hell does that mean? Quite well, it's good to hear. Oh god. Now, Thunder said it's not a big deal if I can't answer this question. Measuring on WWF and racing games. Just I was busy that night, so I didn't watch the stream for very long. But like I clicked on the stream for a little bit, and I saw at least the title was Linear Algebra Reading Group. So I don't know exactly what form that's taking, but yeah, I don't know. But, like to me, the magic of a reading group is being able to like get in Discord with other people and solve things like as a group, like the name says. And so it's great to solve things with you, Fitfinbox, and sometimes Stuki when they're around. But it'd be nice to have like more people who are like involved too. So I don't know. I think it's like the fun of doing it as a group. But again, people might just not be interested in that sort of thing, and that's okay too. Oh, here's the actual question. The time for the ray to travel along optical fiber P is NL/c sine theta, where c is the speed of light in a vacuum. What is the time for the ray to travel along optical fiber Q? The answer is apparently A, which is the same thing as for P. This question's Charles. Yeah. Yeah, I'd never done a problem like this before, I don't think. It's from someone in chat who probably had to go by now, but I love to get back to him. Same at the same angle. Okay, so the difference here is that Q is wider, but the same length. All over after the sands. Oh wow. Horizontal along the fiber is c cosine theta in both cases. Component. Oh, that's it? How could they be? I get that the angle's the same, but isn't the hypotenuse just different? Path P into path Q by flipping a few segments. Oh. Yeah? So again, their light rays and speed of light is constant, but they're... Oh, these triangles are similar, maybe? Oh, okay. Maybe I see it geometrically where... Do I see it though? Transforming P into Q, you have to shuffle / alternate vertical velocity at some points, but the horizontal velocity never changes. Like, we could literally rearrange these line segments to make the exact same picture as with Q. That's what it sounds like. Like, this is gonna look terrible, but I could take this line segment, put it up here, this line segment, put it down here, and we have the exact same path as with Q. Except doing that only requires flipping over the horizontal axis. Right, so instead of transferring them left and right, I should have, I guess, done a vertical flip. Okay. So let's take this. Let's move down here. I like to be able to make a picture that would explain this for Thunder. So if we take a box here, vertically flip this portion, we would get just the third segment. Oh, well, we have to do the third and fourth though, right? I'm not gonna be able to easily flip this in Paint. Like, I'm gonna have to do it the old-fashioned way, I think. Let's see what Paint can do. Rotate. Oh, hey, flip vertical. Ah, look at that. Hey, Phobos. How's it going? Okay. Just the third segment flipped there, and then I lined it up. I hope that was okay. Right. I guess that would be, yeah, okay. We literally flipped it across this line here, and that's why it got translated down as well. Okay. Mention the Q path up to and including the fourth segment. It's matching the Q path up to and including the third segment. Okay, yeah. Trying to make that work in my head. No change in what's going on horizontally. Ford? Oh, you did say Ford, yeah. And so then the next step would be flipping this fourth one? Yeah? Okay. Gonna only require vertical flips. No. Stay red. This is... no, 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 no. I'm not doing a job of... To be a bit more specific about the box that I'm drawing here. Just that bit. I hope this is going to help and not hurt for the explanation here, but... vertically flip the red box across the blue line. This is just an explanation why it's sufficient to only consider horizontal velocity, which is the faster way to do it. Okay. The exact same path as Q, which is why we can just consider horizontal velocity and nothing else. Oh no. Community with only a vertical flip. Yeah, it's important we use only vertical flips. What? Why did I click? What? Are you kidding me, Paint? Okay, fine. As soon as I click out of the box, it suddenly resizes the text and cuts off the bottom. I'm just going to leave that as is. It's a single word that went wrong. So let me copy this, and I'm going to DM this to Thunder. Transform key into Q using vertical flips, which implies we can consider the okay. um was there anything else from chat? Trying to think back. I don't think so. Is critical still here? I guess there was that coding problem. Oh, critical. I'll give it a minute. But if there's another question from someone in chat, I'll probably just call it in. This is a draft book for Morin on Waves. College sophomores. Foray and interference chapter a little more polished than the others. I guess it'll be at least 20, 30 by the time I revisit it and turn it into an actual book. Just following the George R. R. Martin model. My friends chose it. To be honest, I'm not interested in it. I just want to hang out with my friends. It's called like The Killer's Game or something. Let me see if I can find it. The Killer's Game. Yeah. Hey, Bode. So I just look like a normal action movie. But I don't know. Could be cool. Cool, enjoy, question mark? Hopefully, yeah. Yeah, with an exclamation point. You know, maybe the movie will be bad. I don't know. I haven't seen it yet. This will be the first movie that I've seen definitely since COVID started, but even before COVID, I don't remember the last time I saw a movie was in the theater. What would it have been? Oh, has it been since I've been to college? I think I saw like Infinity War in theaters, I think. One of those big Avengers movies. Have I not been to the movie theater since then? Yeah, I can't think of what movie I saw in theaters more recently. Yeah, it's weird to think about. Captain America versus Iron Man. Oh, Civil War. Yeah. Yeah, that was even before me then. It's because we had all the time until a few months ago. What happened a few... do I know what happened to you a few months ago? I don't think you mentioned moving. I don't know. What happened? That definitely once COVID hit, I already wasn't going to movie theater much anyway, and like, you know, in a world with COVID, the movie theater seemed like one of the worst things that you could do. Just sitting indoors with a bunch of strangers for a couple hours. You don't watch movies, music albums are my movies. Oh, nice. I do really like watching like music. I don't know if you mean like music videos, but I personally kind of like watching those. COVID is the best time for me because no one else is there. Okay, that's fair. If no one else is there. That's what Lucas theaters were desperate. Yeah. Everything about music. Oh, that's awesome. I like music definitely it's like a special place in my heart too, because it's just like the effect it has on my mood is really nice. It's kind of nice. I feel like Spotify can't figure out what music I like. So when it comes to finding new music, it's like YouTube recommendations, but even then those kind of suck. So all right. It's 54 hours. I mean, I don't have like one big playlist. I got a bunch of different ones for each mood. It's like one of my rap ones is 4.5 hours. I have a night driving one for an hour and a half. Old music for 3 hours. My good metal playlist is 4.5 hours. My bad metal playlist is 6 hours. I'm probably adding up to around where you are. My random miscellaneous playlist is 6.5 hours. Oh god, I have too many playlists. I call it bad metal, but it's really metal I've listened to. It's either I listened to it in high school and now like it's like a little just like I feel like I've evolved past it maybe, or it's songs that I really liked but I listened to them too much and I got a little bit sick of them, so I just call it bad metal. Yeah. I've got a second rap playlist where I just put a bunch of like entire albums. That one is 10 hours, but it's kind of cheating because I used to listen to that one like it wasn't 10 hours when I listened to it every day front to back, but I listened to it while I was working from home, and it was a good like 3 hours or something. Had a bunch of Juice World and Polo G. Then went into a bit of Kendrick. And that was my background noise for working from home for a good while. Deal with all your songs? Yeah, I don't want to forget about them because I'm occasionally in the mood to listen to them, and I'm going to go crazy if I can't find it. I've got a couple, I got like a Spanish language playlist, I got a French playlist, a Japanese playlist too. Classical playlist. Oh, that one's pretty short, hour and a half. Talking Heads recently. What was their big song? That sounds familiar. Talking Heads. Psycho Killer. Qu'est-ce que c'est? Yeah. That's the only song of theirs that I've heard. My favorite album is Ready to Die by Biggie Smalls. It's an emotional ride. But that's definitely my favorite album. Your shortest place is 25 minutes? Kids See Ghosts by Kids. I never heard of that person. Well, I'm gonna look it up and listen to it. Okay. Oh, it's only 7 songs as well. Not even that bad. Oh, I love Biggie. Cook, I'm probably gonna wrap it up in like a minute or two here. Is there something you want to say though? I definitely have to go in 20 minutes, but since there doesn't do, we're just kind of like chilling right now anyway, so. To sad boy vibes playlist, you only have to be sad for 25 minutes? Hey, you know? If that's all you need, that's a good thing. Actually, you know what? We're just start playing this Kids See Ghosts album. Yeah, sad music is always the hardest to find for me. Because, I don't know, there aren't many sad songs that really, like, hit the spot. And you know what, there's a new Kendrick diss track, and I need to listen to it again. Kendrick Lamar new song. I don't remember what it's called. But this one. I think is it. So if you like Kendrick and you haven't heard this, then you should. First song is kind of weird. Okay. Because I'm not giving it a fair chance. I'm like talking at the same time, so I'm not paying full attention. But I'm gonna listen to this through. Kid Cudi's Plenty Sad. Okay. Um, for me, like a sad song that hits the spot, or at least like rap that doesn't do it for me. But like oh my god. Where is it? Hurt by Johnny Cash. That's a good sad song. It's really sad though. Yeah, it is funny. You like to watch The Throne. My Beautiful Dark. Are those albums? Watch The Throne. Oh, Jay-Z. Okay. I've hardly listened to any of those. Hmm. I mean, I feel bad because this discussion is really cool, but I do need to wrap it up soon. I'm gonna start maybe looking for a raid, see if there's any friends who are on. Um, Here's someone. Oh, well, let's see if this person is gonna keep going for a little bit. Once again, I'm watching the ads. I want to see what happens with this person's stream. Yeah, this song is pretty good so far. Okay. Looks like she's not ending anytime too soon. So let's go and raid. Oh shit, let me cut off the YouTube stream. If you're on YouTube, thank you. Bye.